Welcome everyone to the final day of our conference, Hydrogen Fuel Transport, Integration with Whole Energy Systems. The last day is structured around the challenges in hydrogen transport associated with policy and societal aspects. In case you were not with us in the first 2 days, I'm Tony Roskilly. I'm Professor of Energy Systems at Durham University and a Director of Durham Energy Institute. And I lead Network H2, which is a national hydrogen fuel transportation research network plus that's kindly been funded by EPSRC. Please visit our Net Zero research website to find out more details about the research we fund and the dissemination activities we have been carrying out and will continue to organize. Our last day of presentations takes us to lunchtime. And we are delighted to start with a keynote presentation from a leading energy economist. It's going to be given by Claire Thornhill, who is an Associate Director at Frontier Economics. She is an experienced economist with particular expertise on climate change and low carbon transition. Her experience includes advising clients on investment decisions, business models, design and policy interventions in the low carbon energy sector, including buildings, transport and industrial decarbonization, renewable electricity and carbon capture and storage. Prior to joining Frontier in 2011, Claire worked at the Climate Change Committee and in the Government Economic Service. Claire has a degree in economics and history from Trinity College Dublin and a MSc in environmental and resource economics from the University College London. Over to you, Claire.
Thank you very much. I'm delighted to be here today to talk to you on such an exciting and important topic. So what I'm going to talk to you today is around challenges on the low carbon hydrogen production side. I'm just going to start off before I get into the slides, just give you a little bit of information on Frontier Economics. So we are an economics consultancy with offices across Europe. Our main office is in London, but we've also got offices in Dublin, Madrid, Cologne, Berlin, Brussels, Paris. I think that's everything. And we have about 300 economists working across all sectors, so not just on energy and climate change. We do a lot of competition and regulation work as well. In the low carbon hydrogen area, we've been working for kind of, I guess, it must be around sort of 7 to 8 years now on low carbon hydrogen topics, both on the continent and in the UK and Ireland, from a range of different perspectives. So my own work started for BEIS, the UK government department, looking at business models for hydrogen and the kind of market frameworks that might work in a low carbon hydrogen world. And then since then, I've also worked for bodies like the Energy Systems Catapult, looking at the regulation that might be needed for networks and storage, but also on the investor side. So helping potential investors in hydrogen understand where their markets might be and how they might gain revenue given the policy framework. And more widely, we've worked for gas networks, investors on the continent. We've also developed some low carbon hydrogen strategies for countries. The last one I was involved with was in Northern Ireland. So just thinking about how quickly they can get a low carbon hydrogen economy off the ground. That's a bit of background. What am I going to talk about today? Really 3 points that I wanted to cover. The first is around incentivizing investment in low carbon hydrogen. Why is it challenging? Why have we ended up with such a complex array of policies? And I've got a few slides on that. Then we'll get into some of these policies. So mainly focused on the UK, but I'll also touch on the policies that are in place. 3 European countries that have the most advanced policies in this area, being Germany, the Netherlands and the UK. And then I'll just end on a slide really setting out what this might mean for transport decarbonisation and particularly the use of hydrogen in transport. So let's start with the ambitions. There are huge ambitions to deliver a low carbon hydrogen economy in the UK and in the EU. In the UK, there's a 2025 target to get a gigawatt of electrolytic hydrogen in place. And by 2030, there previously was a 5 gigawatt low carbon hydrogen target, but the recent British Energy Security Strategy doubles that to take it to 10 gigawatts and also specified that 5 gigawatts of this should be electrolytic hydrogen. And obviously this British Energy Security Strategy was written in the context of the current gas price crisis, which probably informs the kind of emphasis change to electrolytic hydrogen. And beyond 2030, there is an aim for large-scale deployment of hydrogen to reach all hard-to-decarbonise sectors. One thing I should mention, there's a big uncertainty in the UK around the role of hydrogen for heating in homes. That's something that we're working for BEIS on at the moment. So BEIS has a huge programme of research and technical research going on at present to inform a decision in 2026 about or the extent to which hydrogen makes sense as a low carbon fuel for heating buildings. But there is a really strong consensus that hydrogen will be required in certain sectors like heavy industry. What is the intention in the EU? So the EU launched their strategy on hydrogen in 2020. And again, we've got really ambitious targets here. So 6 gigawatts of renewable hydrogen installed by 2024 and 40 gigawatts of renewable hydrogen by 2030. And what we've seen at EU level is much more of an emphasis on green hydrogen, though some individual countries are also going for blue. So that's the intention. What's actually happening? The chart at the bottom of the slide sets out announced green hydrogen projects in the EU and the UK. So this comes from some analysis by Delta EE, which was published in February 2022. So more may have happened since. And this is based on announced projects. So not all of these projects will have reached final investment decisions. I think, for example, for that 2 gigawatts in 2023, about a quarter of them have reached final investment decisions, were sort of classified as firm. So what you can see here is that an enormous ramp up is needed from the installed capacity at the end of 2021, which was 118 megawatts, according to Delta EE, to the kind of level that's required by 2030, so 50 gigawatts across the EU and the UK. So this is a really kind of radical step up. Major policy action is going to be required to deliver it. Why is incentivizing hydrogen hard? The last 10 years in Europe and the UK have seen, as you'll all know, major progress in getting renewable electricity off the ground. And we've learned a lot about how best to incentivize renewable electricity. So early schemes, such as the ROC scheme in the UK, were quite costly for the taxpayer or the energy consumer. And as time went on, we learned how to design better and fairer policies that incentivized efficient investment and a kind of efficient allocation of risks across energy consumers, taxpayers, and investors. But hydrogen brings another challenge, and it's these are kind of obvious points to make, but actually quite often get forgotten in the policy discussion, particularly when we're drawing parallels to renewable electricity. So starting on the right here, the key kind of thing here is that hydrogen is not a direct substitute for the incumbent fuels in most of the applications that it's being used. So there are obviously some industrial applications where hydrogen is replacing grey hydrogen, where low carbon hydrogen is replacing grey hydrogen. And in those cases, the proposition is much more similar to the renewable electricity proposition. But generally speaking, those investing in hydrogen are facing highly uncertain demand for low carbon hydrogen. And what's more, that demand is largely policy driven. So this is the chicken and egg problem that people talk about in the low carbon hydrogen sector. In order to invest in hydrogen, you have to have confidence that the demand will come online, and that is not something that you can develop confidence in using kind of market intelligence. It all depends on policy actions that will be taken. Then on the left-hand side, there's huge uncertainty around the costs of the production technologies. Those production technologies have different levels of maturity, Methane reformation has been used for years and years, but pairing it with CCUS is quite new. Electrolysis, again, is a well understood technology, but huge advances are being made all of the time. What that means is that learning externalities are difficult for investors to capture in the market. So without policy support, they will underinvest. And those learning externalities vary quite dramatically across the technologies. It's worth also saying that, a couple of years ago, the expectation was that methane reformation would be much more cost effective than electrolysis. That I think even the BEIS electricity or hydrogen production costs that were published recently, they thought that the only kind of electrolysis technology that could compete with blue hydrogen would be where electrolysis would be using curtailed wind. Now that's only in the near term. Obviously, over time, the expectation was that the cost of electrolysis would come down, but in the 2020s, it was thought that blue hydrogen would be a lot cheaper. That's all a bit up in the air now, given the high gas prices, and I think there's a lot of uncertainty. I haven't yet met someone who knows where gas prices are going over the medium to long term. There's uncertainty on the production side, there's uncertainty on the demand side, and then, of course, because of this issue about hydrogen not being a direct substitute for the incumbent fuels, it cannot just be put into the networks, or at least it can to some extent, but additional investment in hydrogen and transport and storage will also be required. And that network investment will require some degree of coordination, given the natural monopoly characteristics of networks. So that's another element of complication when getting this whole economy off the ground. So what does that mean? It means that generally when economists think about trying to get a low carbon energy market in place, we will start off with thinking about what the efficient end state would be. And here we would think, looking at the right, that we would have a market where there are no subsidies and the only intervention is to internalize externalities, for example, with the carbon price. But we're so far away from that at present. There's a lot more barriers and market failures in place. So in the short term, we're in a world where there's learning externalities, there's the chicken and egg problem that I mentioned, there's policy risks across the value chain. Therefore, the priority has been in developing policies in getting initial investments off the ground, getting infrastructure in place to enable the markets and delivering learning. And that means, as we'll go on to talk about, that policies have tended to be complex and also slightly imperfect in places. And I think there's learning on the policy making side as well as in other areas of the market. So these challenges are driving the introduction of complex policies. So looking just at three countries, as I mentioned, the UK, Germany, and the Netherlands, what we have seen yet is that unlike in the world of renewable electricity, where a sort of broad consensus around production subsidies has emerged, there isn't yet a consensus in Europe on the best instruments to incentivize low carbon hydrogen beyond R&D funding, which all countries are engaged in. And that means that actually not only are there very different subsidies across countries, there's actually a mix of subsidies within countries. And I think that reflects the fact this kind of multiplicity of market failures and barriers that are in place. It's very hard to design one all singing, all dancing policy that corrects for all of those. So on the production subsidy side, the UK has announced a variable subsidy, which is originally aimed at delivering hydrogen, large-scale production of hydrogen for industry, and also a capital grant scheme, which is initially focused on electrolytic projects. And I'll go on to talk a bit more about both of those in a moment. The Netherlands has introduced a carbon CFD scheme. So that is a top-up payment against the carbon price, so that investors have certainty over the revenue that they will, or I guess the revenue that they can potentially receive in the carbon market. And the Netherlands also has investment support for electrolyzers. So Germany has gone down a different route, and actually the German hydrogen strategy has many, many measures in it, but just to pull out a couple of the key ones. So Germany is piloting a carbon CFD on the demand side. So this is where users of low carbon hydrogen will receive a top-up payment on their avoided carbon costs. Again, this is meant to incentivize the use of low carbon hydrogen, but here focusing on the demand side so that users will be willing to pay a higher price for that low carbon hydrogen. The UK is also thinking about the end user side and has some capital subsidies in place. So in the kind of debate around how to incentivize low carbon hydrogen, there tends to be a range of categories that of options that come up. So one is the kind of the simple carbon price, and as mentioned, that could be a long-term aim, but it's too early for that now, given all of the different barriers and market failures in place. The next are the subsidies for production and end users. Then another instrument that comes up all the time is the option of an obligation. So this is where end users or suppliers are obliged to consume or produce a certain proportion of low carbon hydrogen as part of their fuel mix, and where that is certified using certificates which can be traded. So those that find it easiest to switch to the low carbon options can do so, sell any excess certificates to those that find it very difficult. And obligations were used quite a lot in the early stages on the renewable electricity side. And there is an obligation in the UK, the Renewables Fuel Transport Obligation, which I'm sure most of you are really familiar with. And there's also in Germany plans to introduce a quota for e-fuels in aviation fuel. But the issue with obligations was revealed in the experience of applying them in the renewable electricity sector, is that unlike the kind of contractual instruments around which subsidies tend to be based, where the parties can sign a contract, government-sponsored third party, obligations tend to be non-contractual, and governments have had a history of intervening in them over time. So, for example, changing the level of them, imposing buyout prices, and generally all of those, or that risk that governments will intervene, makes it difficult for investors to bank against these types of instruments. And we've seen that in the response of industry to BEIS's recent consultation on business models. That point about obligations being not very bankable was made again. So I'm going to come on to talk a little bit about support for imports as well, because there's some interesting developments on that in Germany. Great. So I mentioned innovation funding, and innovation funding is a major source of funds for low carbon hydrogen projects in the EU. And the big scheme, and it may be that some of you are already involved in this, is the Important Projects of Common European Interest framework. So that allows member states to finance investment in areas, including in low carbon hydrogen, so long as those projects involve at least 2 member states. And there has been a large number of projects working their way through this kind of filter. And finally, you'll see there, I think there's a list of around 40 projects have been approved across 15 member states to receive 5.4 billion of government support. And those projects are around production, fuel cell technology, storage, and end user technologies. This framework, we believe, will be a major driver of getting some of these initial projects off the ground. So a little bit more about what's going on in the UK. So in the UK, BEIS is proposing a variable premium price support mechanism, as well as CapEx support, which initially, it says green hydrogen here, but it should say electrolytic hydrogen, which initially is for electrolytic hydrogen. So on the hydrogen business model, the basic structure is that a strike price is agreed, which gives the per unit price that the producer will receive for each unit of low carbon hydrogen that is sold in the market. How the mechanism works is that the producer receives a top-up payment or pays back according to the difference between that strike price and the reference price. There's a few complications in this that are still being ironed out. So BEIS has kind of put out its initial thoughts on this, and some of the more the detailed elements are expected to be finalized, I think, this year. So one of the elements that is still a bit uncertain is something that BEIS is calling a sliding scale. So I mentioned previously that producers face an enormous amount of demand risk. So if you're sinking several £100 million in a big low carbon hydrogen production plant, you need to believe that BEIS is also going to or that policymakers and regulators are also going to put the conditions in place for the demand side, as well as helping you with supply. And that leaves a lot of demand risk with investors. And when we worked on hydrogen business models for BEIS back in 2020, investors described that as a sort of existential risk. So it's not something that just increases their cost of capital. It's something that actually means that they just hesitant to invest. In some other sectors, we've seen this overcome by giving investors some funding to cover their fixed and capital costs, no matter whether that demand ensues. What BEIS has gone for instead is this thing called a sliding scale, where the producer will receive a higher strike price for initial volumes. But there's very little detail so far on what this will actually involve. So I don't think we're at a point yet where investors can say what exactly this sliding scale means and really confirm that it overcomes this major risk. The other big uncertainty is around the reference price. And I think this is very relevant for the transport sector as well. At present, BEIS has said the reference price will be based on an achieved sales price with a floor at the natural gas price. What that means essentially is that the investor will, at a minimum, be topped up by the difference between the natural gas price and the strike price. But if the producer sells low carbon hydrogen for a higher price than the natural gas price, they will be topped up by a smaller amount in line with the difference between the achieved sales price and the strike price. Now, that begs the question of why investors would really seek to get a higher achieved sales price when any kind of difference between the natural gas price and the achieved sales price will simply result in a reduced top-up payment. So BEIS, in their business model document, have described some price discovery mechanism that will help incentivize producers to seek a high achieved sales price. But it's a bit light on details at the moment, and it's not very clear how that exactly will work. And I guess the reason that the choice of the reference price as the natural gas price makes a lot of sense, because if you think of the main customers of the initial low carbon hydrogen as currently being consumers of natural gas. And also, when this was originally conceived of, it was thought that the majority of early producers would be blue hydrogen producers. And they're already obviously involved in the natural gas market because natural gas is one of their key inputs. Where a natural gas reference price causes potentially some complications are when we're talking about electrolytic hydrogen, and also when we're talking about hydrogen producers that are selling hydrogen into other markets where natural gas isn't the incumbent fuel. And at the very least, this just means that low carbon hydrogen producers, they need to be engaged in the natural gas market, given that the price of natural gas will be a key determinant of the top up they receive. This could cause some issues for small projects and risks for small projects, and also for projects that are not linked to the natural gas market in any other way. So that is the hydrogen business model. BEIS has also launched the Net Zero Hydrogen Fund, which is going to provide up to 240 million across 4 strands. So the first 2 strands are active at the moment, and Strand 1 is around feed and post-feed studies, and Strand 2 is around CapEx support for projects that are not going to receive hydrogen business model support. However, Strand 3 and Strand 4 will allow interaction with the hydrogen business model, so it will be possible to claim both types of support. So I mentioned also the renewable transport fuel obligation. So that also, in theory, incentivizes hydrogen. So the RTFO is a tradable obligation scheme, and hydrogen produced by electrolysis using renewable electricity or from biohydrogen can receive support from this scheme. So basically the obligation applies to suppliers of fuels to transport, and including maritime and rail now. And there are kind of two parts to the obligation, and one of the parts relates to development fuels, and hydrogen is one of the fuels that's allowed to meet that obligation. But actually, looking at the 2022 renewable fuel statistics that have been published to date, it seems that no hydrogen so far has been used to meet those development fuel obligations. It has mainly been fuels derived from waste that has been used to meet that part of the obligation. So why has the RTFO been slow to incentivize hydrogen so far? So one is the point that I mentioned previously, that the RTFO is an obligation scheme. Investors have often pointed out that these obligations are hard to bank against, given the risk that governments will change the parameters, change the size of the obligation, change the buyout price, and so forth. And in fact, that's something that we've seen quite recently. So another element is that until the rules were changed in 2021, only hydrogen with a direct connection to renewable production counted for this scheme. So now the rules have been changed to allow the purchase of renewable electricity via PPAs, and that potentially will open up a bit more use of hydrogen in the RTFO. It's also worth noting that demand for pure hydrogen for vehicles is relatively low at present. So I'm sure there's many participants here will have more up-to-date numbers than this, but in 2021, BEIS noted that there were around 300 hydrogen vehicles on UK roads. So we're still talking very small numbers. And then finally here, that heading is incorrect. It should really relate to the bankability. So essentially the price of certificates traded under the RTFO can be very difficult for investors to predict. And that's something, again, that makes the RTFO less easy to bank against. So for example, in 2020, the government decided to increase the buyout price. The buyout price is the amount of money that fuel suppliers can pay to kind of buy out their obligation rather than to actually purchase the green fuels. So a decision to increase the buyout price essentially increases the price of tradable certificates under the scheme. But of course, there's always a chance that the government will reduce the buyout price as well. And all of that affects investors' confidence in the revenue they can gain from a scheme. So worth also mentioning that there's innovation funding in place on the demand side in the transport sector in the UK. Just to mention on the import side, so I touched on this earlier, but there's some really interesting developments in Germany on imports. So Germany envisages that the majority of its hydrogen will come from imports. Germany is focused on green hydrogen and has set up something called H2 Global. And this is basically an organization that will buy and sell imported low carbon gas. And there will be a kind of CFD approach where the difference between the supply prices and the demand prices will be compensated by grants from the German government. And this is quite exciting, I think, because there's a really strong green hydrogen production potential in countries with great renewables. So people talk about Morocco, Chile, places like that. It will be interesting to see what H2 Global does to that market. So just to circle back and conclude, what does all of this mean for transport decarbonisation in the UK? So worth saying that BEIS expect transport to be a major user of hydrogen. The idea is that in the 2020s, before the kind of refueling network is up and running, the main focus will be on depot-based transport, which could include buses. In the 2030s, then there could be an expansion to HGVs, buses and rail, and also the potential for use in commercial shipping and aviation. And then, of course, there's just huge uncertainty about what happens in the long term. But there are still many open questions around this. Obviously, for transport to use hydrogen, the hydrogen production has to be up and running. And there's still some uncertainty about the speed, the location, and the nature of the hydrogen production that comes online. I think there's still, as I mentioned, a few kind of key issues to iron out around the business models. So the impact of the reference price and other business model design questions such as the sliding scale. One thing I didn't mention was the low carbon hydrogen standard. So that is the standard that needs to apply in order for the hydrogen to be eligible for any of these production subsidies. And at the moment, there are some slightly kind of anomalous conditions in that, or at least conditions that may be expected to develop over time. So for example, for a green hydrogen producer using grid electricity, the decision on whether or not that counts as green will be based on the average intensity of the grid, the electricity grid at any point in time, rather than the marginal intensity. And obviously that it's much more practical to use the average intensity, but that could also result in the near term in electrolytic hydrogen being produced based on a grid that is using natural gas at the margin, which is sort of really efficient outcome. So I think we would expect changes to that over time once those initial investments are up and running. So then there's uncertainty over the location and timing of production. As mentioned, there's been currently a focus on industrial clusters and getting the first blue hydrogen off the ground, but actually that might all change with this focus on electrolytic hydrogen that's come in since the gas prices. And there's, as I started off with that delta EE chart, which showed just how much scaling up is required over the next few years, and there's a huge uncertainty over the extent and speed that will come on. And I also mentioned there's still uncertainty around the uses of hydrogen in the economy, particularly around heating. And I think were heating to be a kind of target for hydrogen, that will completely, or heating buildings, that will completely change the whole hydrogen economy as well, and will have knock-on impacts for transport. That is all from me. So I think I will hand back over to you, Tony.
Thanks very much, Claire, for a very comprehensive presentation. Our next presentation is on a business model design for hydrogen refueling stations, a multi-level game approach. Tian Zhao is from Copenhagen Business School. He's a PhD candidate. Previously to his studies here on energy economics and policy was at Beihang University in China. He has already published a number of papers on the economic and policy impacts of climate change, specializing in the application of game theory. Over to you, Tian.
Thank you, Tony, for your introduction. Hello, everyone. Today I want to present our recent working paper, whose title is a business model design for hydrogen refueling stations, a multi-level game approach. And this work is with Professor Liu and Professor Yamash. The background is a hydrogen value chain in terms of transportation, mainly includes two stakeholders: the hydrogen manufacturer, either the centralized hydrogen production plant or decentralized on-site hydrogen refueling stations, and the other stakeholder is hydrogen retailers, that is off-site hydrogen refueling stations. After the hydrogen is produced, it will be transported to the demand side, the off-site hydrogen filling station, through the trucks or through the pipelines. But we have two questions about this value chain, because there are two major actors, the hydrogen manufacturer and the hydrogen retailer. They can choose operate their business separately, or they can also choose run their business jointly. So the first question is that which business model is better to generate more profits for them? And for the first question, we use the Stocker game and the cooperative game to respectively calculate their profits in the case of separate operation business model and in the case of joint operation business model. And after the calculation, we can compare their profits under different business model, and we can find if they choose joint operation as a correlation, they can get more profits than they choose separate operation. The second question is, if we have shown the joint operation business model is better, but how to make the two actors really adopt this kind of strategy? Because when it comes to the joint operation, it will cause a kind of coordinated cost, such as they need to make an agreement, they need to design a contract. It will cost communication cost, negotiation cost. So in terms of this cost, the two actors may hesitate to choose the optimal business model of joint operation. So the second question is, after we have shown the joint operation business model is better, how to promote this kind of business model being adopted. So we use for the second question, because this is a dynamic decision making. So we use a dynamic game called evolutionary game to solve this dilemma. And we found if we can increase the initial willingness of choosing the business model of joint operation, and if we can reduce the relevant coordinated cost, the whole game will converge to the ideal equilibrium we want to get. That is, the both of actors want to choose run their business jointly. So there are two major contributions. The first one is that we try to explore the optimal business model for the value chain of hydrogen fueled transportation. And the second one is we will design a business model as a multi-level game, including Stacker-Burger game, cooperative game, and evolutionary game, providing a new perspective for similar analysis. Because the previous research only used one-level game or two-level game, but in our paper, we not only study how to find optimal business model, but also find how to make this kind of the optimal business model being adopted by the actors. So we give some basic assumptions. We assume there are two major actors. There is one hydrogen manufacturer and one retailer that is a hydrogen refueling station. And the parameters used in this model are shown as follows. The P is the retail price that consumers pay to the hydrogen refilling station. W is the wholesale price that the hydrogen refilling station pay to the hydrogen manufacturer. And C is production cost of hydrogen per kilogram. And Q is the demand of hydrogen from consumers. And we also assume a linear demand curve that is Q is equal to A minus BP, where A and B are constants. And as for the profit functions, if the two actors choose separate operation, they will get their maximum profits individually. So for the hydrogen manufacturer, its profit function is the wholesale price minus the cost of hydrogen production. The first part means profit margin per kilogram, and we multiply the profit margin times Q, that is the total profit for the hydrogen manufacturer. For the hydrogen retailer, the hydrogen filling station, the P is the retail price. The retail price minus its wholesale price should pay is the profit margin for the retailer, and we multiply the profit margin to its demand, and we get total profits for the hydrogen retailer. And if they choose the business model of joint operation as a coalition, they will get a collective profit function. That is the retail price minus the cost of hydrogen times the demand. So we start with the game by starting the business model of separate operation with Stacker-Burger game. Under this business model, the hydrogen manufacturer supplies hydrogen to a hydrogen refilling station as the leader because it determines its wholesale price first, and the hydrogen refilling station obtains the hydrogen and retails the hydrogen to consumers as a follower because it cites its retail price after observing the price set by the manufacturer. The reason why we use Stackelberger game for this case because the Stackelberger game is a sequential leader-follower game in which the leader moves first and the follower moves after. They can decide their quantity or price, and they also maximize their own profits with no operation between them. So we use the backward induction to solve this game, to obtain their respective maximum profits. And the profit maximization arises when first-order derivative of profit functions with respect to price is zero. Here we rewrite the profit function for the hydrogen manufacturer and hydrogen retailer again, because this is called backward induction. So we first to calculate the first-order particle derivative of price in the equation 2 and let this derivative be 0, and we get the equation 3. And then we for the equation 1, we let the first order particle derivative of the wholesale price be 0, and we get equation 4. So we combine the equation 1 to 4, and with some easy calculations, we can finally get the maximum profits for the hydrogen manufacturer and hydrogen retailer, respectively, which are shown in the equation 5 and the equation 6. And now we move on to the second game to study the joint operation business model with cooperative game. In the case of joint business model of joint operation, the hydrogen manufacturer and the hydrogen retailer are one coalition. They pursue the maximization of its collective profit. And we rewrite the profit function under the business model of joint operation again here. That is, we use the profit margin times the demand. Likewise, the profit maximization arises when first order derivative of profit function with respect to price in the equation 7, and we can also easily find the maximum profits of the coalition. That is shown in equation 8. Now we get the total collective profit for this coalition. Now, for the business model of joint operation, the members of the coalition can sign an agreement or a contract for allocation of this maximum collective profit between themselves. But how to allocate this profit? We use CP value to the question of profit allocation. It is calculated by considering all the possible orders of the arrival of the players into a room and giving each player his marginal contribution. We look at this table. We set the hydrogen manufacturer as the player 1 and the hydrogen retailer as the player 2. In the first case, if the hydrogen manufacturer go into this room first, the marginal contribution from the hydrogen manufacturer is the profits is the profit of separate operation. And then the player 2, the hydrogen retailer, go into this room later to become a coalition, and the marginal contribution from the hydrogen retailer is the collective profit minus the profit of separate operation of the hydrogen retailer. So the second case is likewise, and both cases has the same probability, that is 0.5. So we use the probability to times its corresponding payoff. We can calculate the allocated profit for the hydrogen manufacturer and hydrogen retailer in the context of the business model of joint operation. So we can compare the results of the equation 9 and equation 10 with the profit obtained in the case of separate operation. And we find the profits of these two actors under the business model of joint operation are greater. We can conclude this joint operation business model is better than separate operation because it can generate more profits for the actors. And now we move on to the last game to study the strategy adoption with the evolutionary game. From above slides, we have known the joint operation is an optimum business model for the value chain of hydrogen transportation. But the process of being a coalition could generate extra coordinated cost, which may cause the manufacturer and retailer not to cooperate. So we aim to investigate these actors' dynamic interaction to explore how to make them finally adopt this optimum business model of joint operation. For this question, we use one dynamic game, which is called evolutionary game, which is widely used to solve this kind of dynamic decision making. And we this payoff matrix under the case of evolutionary game. The C means the coordinated cost. The N is the distribution coefficient of the coordinated cost. And X, Y are respectively the probabilities of relevant strategy. For example, if both of them choose the business model of joint operation, they can get the optimal allocated profit, but they also need to pay their allocated coordinated cost by themselves, like this first element. And if either of them choose not to adopt the joint operation business model, both of them cannot get the optimal allocated profit in the case of joint operation. The actor who chooses joint operation needs to pay its own coordinated cost. And if both of them choose not operate jointly, they will get the profits in the case of separate operation, respectively. So to solve this evolutionary game, we use the replicator dynamics because the time is limited. So I will skip the details about how to solve this equilibrium. Finally, we can get there will be two equilibriums. These two actors will both choose the business model of separate operation, or they will both choose the business model of joint operation. So this equilibrium of joint operation is the ideal equilibrium we want to get. So how to make this dynamic game converge to this ideal equilibrium? We use the sensitivity analysis of the key parameters in the game model, and we found if we can increase the initial willingness of each actor choosing the business model of joint operation, and if we can reduce the relevant coordinated cost, we can promote this kind of dynamic decision making to the ideal consequence we want to get. That is, both of them will be willing to choose the strategy of the business model of joint operation. So we move on to the conclusions and the outlook. In this working paper, we proposed a multi-level game framework for the design of a business model of hydrogen refueled transportation. And for the value chain of hydrogen refueled transportation, the optimal business model is the joint operation as a coalition compared with the separate operation as individuals. If we can decrease the coordinated cost, and if we can increase the initial willingness of operating jointly, we can lead the whole dynamic decision-making game to the ideal equilibrium. But this working paper has some limitations for future study. The first one is we simplified the supply chain as one leader, one follower. That is, we assume there is one hydrogen manufacturer and one hydrogen filling station. But in reality, it can be one leader, that is one hydrogen manufacturer and multiple followers with many hydrogen refilling stations. The hydrogen manufacture can be centralized or decentralized. In different scenarios, the profit function or the demand curve may be different. The second one is if we can consider the competition between the hydrogen refilling stations, and if we can consider the different colors of hydrogen produced in the hydrogen manufacture, this work can be more comprehensive. And this is also two directions for the future study. And that's it, Tony.
Very much. So our next speaker is Sally Springer. Sally is a research associate in the Institute of Energy and Climate Research at Research Center Julich in Germany. Her research interests includes social life cycle assessment, corporate social responsibility, sustainability, human rights, and the textile industry. She holds a degree in business administration and a master's in life cycle and sustainability. Over to you, Sally.
Thank you very much. So it's an honor for me to have the chance today to present you my research results. Yes, thank you for that introduction. And the research I'm working on at the moment are the social impacts of fuel cell electric vehicles. What is the motivation behind that? Every one of us knows we have the climate crisis now as a huge challenge to address, and we have the mobility transition. I don't want to talk so much about this because every one of us knows this. And then we have fuel cell electric vehicles, which offer many advantages, also disadvantages. But as we have heard in the last few days, they have a high potential, especially when it comes to environmental aspects. But to name some of them, they can replace fossil-based cars, of course. They can accelerate electrification. They are faster in refueling, and so on. But we asked ourselves, what about the social impacts? Because these social influences and social aspects are one inherent part of sustainability, and it's really important that we don't forget about them. So the presentation today is structured like this. In the beginning, I will provide some technical information about the fuel cell electric vehicle we looked at in our case study. And after that, I will talk about the methodology of social life cycle assessment. After that, I'm going to present the results, the social impacts, and in the end, a short summary, some limitations, and some future research needs. So let's start with the technical parameters of the fuel cell electric vehicle. We assume that the car consists of the 5 components, which you can see here, which is the battery, the electric motor, and the glider, of course, the hydrogen tank, and the heart of the car, the PEM fuel cell with a stack and a balance of plant. The technical parameters were derived from 2 other studies, from Benitez et al. And Miotti et al. They did an environmental assessment and we build upon this. Now, I've mentioned this method of social life cycle assessment, and to give you a hint about what it is, or first of all, we can ask what does life cycle mean? So it's a life cycle thinking approach, and this means that the whole life cycle of, for example, a product is considered, starting with the raw material extraction from either primary or secondary sources. Then the next phase is the processing and production, which usually consists of different steps. Then we have the packaging and distribution. We have the actual use phase of the product. In this case, this would be the driving of the car. And then in the end, we have the end of life, which could be a disposal or recycling or whatever. And along that life cycle, I need different kinds of inputs. Of course, I need materials, I need energy, but I also need labor in terms of working time, for example, and I need money to do that. And then at the same time, at every step of the life cycle, I have outputs. This is in the end, of course, my final product, but also intermediate products. But then next to them, I also have outputs like waste and emissions. I have my revenue and I have social impacts on different kind of people. So now we know what this life cycle thinking is about. And to put it in a greater context, so in the end, I could always do a life cycle sustainability assessment covering all three pillars of sustainability, of which one is life cycle assessment, which addresses the environment and the ecological part. Then I have life cycle costing, addressing the economic issues. And then I have social life cycle assessment, what I looked at now, which covers all the social aspects. And these social aspects can either be positive in terms of opportunities, or they can be negative in terms of risk. Now, social life cycle assessment as a method, there are different documents about it, but there's like a guiding document which is are the guidelines of the UNEP, which we built our approach upon. And this table comes from that document, and we can see here that the word social addresses different kind of stakeholder groups. This can be the workers who produce the product, but it can also be the local community of which the company is surrounded, or it can be the society as a whole, or a value chain actor like a supplier, for example. And then for each of those stakeholder groups, there are different subcategories and impact categories defined. For example, freedom of association and collective bargaining. So we have quite a high variety of different potential social impacts. Now, the social life cycle assessment methodology is an iterative assessment, and it follows the 4 stages, which you can see here, usually beginning with the goal and scope phase. And in this phase, you prioritize which stakeholder group you want to address, or which is most important for your own study now. So for example, you could choose here that you now want to look at worker. Of course, it would always be the best to consider all stakeholder groups, but now in our case, we have chosen the stakeholder group of workers. And then what you do next is you make a prioritization of the subcategories, because as I said, there are quite many of it, and all of them are important in some regard. So again, you prioritize what you want to consider. For example, freedom of association and collective bargaining, or respect of indigenous rights, and so on. Now, in our case, there was a law passed in Germany last year, which is the Act on Corporate Due Diligence in Supply Chains. And next to human rights and some environmental aspects, it has its focus on working conditions. So this was the reason why we looked into the ILO key areas for working conditions. And we looked what is considered there. and then we translated those topics into the categories for social life cycle assessment. In this case, these categories came from the PSILCA database, but I'm going to tell you more about that later. And here you can see a more comprehensive overview at what we considered in our case study. So as said before, we have chosen the stakeholder group of workers and looked at the subcategories association and bargaining rights, trade unionism, fair salary, gender wage gap, and weekly hours of work. What we can see here is that every impact category is measured with at least one indicator, but for some of them, more than one indicator is used for the calculation. Now, in the goal and scope phase, again, there are other things which have to be defined. For example, the boundaries for the product system have to be set, and you have to set a quantitative reference. This quantitative reference is called functional unit, and in this case, it is the production of a fuel cell electric vehicle with a 100 kilowatt proton exchange membrane fuel cell. So this is the reference for the whole calculation. And we considered or assumed a production volume of 1,000 pieces per year, and the main manufacturing country being Germany. This means that the components, which you can see over there, are produced in Germany, but the supply chain comes from all over the world and from different countries. The life cycle stages we have considered was the raw material mining and the processing and production phase. This was mainly due to constraints on data availability. So the next phase is the inventory in the social life cycle assessment. And this is basically all about the data. And this data can either be quantitative, semi-quantitative, or qualitative. And if it is qualitative, it has to be translated in semi-quantitative or quantitative terms, so in order to calculate it. And the data can either be site-specific, coming from a company, for example, or it can be generic data, and generic data is provided by different databases, and usually the data is on the level of processes, sectors, and divided into different locations, in this case, countries. And in our specific case now, as I've mentioned before, we have used a generic database called PSILCA, and this database is built on another database, which is called EORA, and this is a global multi-regional input-output database, which actually uses economic values. So this is where the whole data came from. Now, the next phase is the impact assessment in the methodology. And we have used a reference scale approach to calculate the results. And I will explain that on the next slide. But to stay here for a moment, in that approach, the calculation is based on risk levels and characterization factors. So for each risk level, I have this factor which serves as a weight. And in this case, the higher the risk gets, the more weight is put into the calculation. But next to that, the calculation is also based on the amount of working time spent. As I've mentioned before, labor and working time is always an input to different processes. And in this case, the working time reflects the relative significance of a process. This means if I spend more time on a process, it get a higher weight in the calculation. And then the third aspect which goes into the calculation are the prices of the components and production steps. Now, what is the reference scale approach and what does it mean? As I said before, we have different kind of impact categories, for example, fair salary. And then I can have one or more indicators to measure that impact category. And for each indicator, I have raw data, for example, $600. But now I don't really know if this is a good performance or not, or if this is high or low. And this is why I can use a reference scale. for example, this one, which is provided by Psilka as well. And now I can see that 600 has a high risk. So this means there is a high risk of not meeting the living wage. And what I have in the end is a risk assessed indicator, which goes with that specific characterization factor, which we have seen before, into the calculation. Now the last phase, or the fourth phase, is the interpretation of the results. And this is what I'm going to do now. So the results of our study were that if we look at the fuel cell electric vehicle as a whole, we can see now that the PEM fuel cell contributes most of the risk. And this is true for all 5 impact categories. So the highest risk stems from the PEM fuel cell. Now, with the help of that, we could identify our first hotspot here. And knowing that, we have deepened the analysis and looked at the PEM fuel cell now with a deeper look. And what you can see here is that the blue and greenish colors belong to the stack, and the yellow and orange color is the balance of plant from the fuel cell. And we can see that across all impact categories, the stack contributes slightly more than the balance of plant, except for association and bargaining rights, where the balance of plant has a higher risk share. And what we can also see is that the membrane accounts for the highest risk share across all impact categories. So the membrane is one major hotspot when we look at the PEM fuel cell. And what we can also see here is that the control in the balance of plant for association and bargaining rights also has a high risk share. Membrane seems to be the major hotspot. Now we can look at the results also from a different angle, and we can see from which countries the risk is coming from, or how the risk distribution across the countries. And this is quite interesting because for the impact category association and bargaining rights, all the risk is coming from China. Now, if we look at the other impact categories, especially for trade unionism, fair salary, and gender wage gap, Germany is the main contributor of risk. And we can ask ourselves now why this is the case, because we are looking at working conditions, and Germany has a strong employment law and also strong law enforcement. So we now have to find out why the risk levels are so high in Germany. And I want to give you an example for that, which is fair salary. As we have seen before, we use 3 different indicators to calculate that impact category. And one is the minimum wage, for which we have a very low risk. Because in Germany, there's this law that you have to pay the minimum wage, and companies are forced to do it. And it's not a big issue. We have a very low risk here. And then the second indicator is the sector average wage, for which we also have a very low risk, because the wage is in line with the sector average. But then we have that third indicator, which is the living wage. And for that, we have a very high risk. And this is the case because the costs of living in Germany are quite high. And in this case, the wage is not high enough to fulfill a decent life. And because that very high risk level gets a higher weight in the calculation, this is how the high risk in Germany comes about, or one reason for it. We can look at a second example, which is the gender wage gap. And here it's a slightly different story, because it's only calculated with one indicator, which has a very high risk. So we know that already. But then we can ask ourselves what kind of data is actually used to calculate that impact category. So the Psilka database is using data from the ILO-STAT database. And this data is unadjusted. This means that aspects like the qualification of the job or the job position, the working time, etc., they are not considered. But if I want to have a clearer understanding of the gender wage gap, it would be advised to use adjusted data. But in this case, it was not, or it is not available across all sectors and countries. This is why the unadjusted data is used. So I can keep in mind now that I have a hotspot here, but I also have to keep in mind that the data is not the perfect one in order to measure that impact category. At this example, we can see that we can gain a lot of knowledge from that method, but that we also have limitations, especially when it comes to generic data, because they may be subject to uncertainties. We also have to keep in mind that the data, this generic data, is sector-specific, not component-specific. And we should not forget that the influence is driven by the risk level, which is predefined, that it is driven by the worker hours. And at this aspect, we can question if worker hours is a good variable to reflect that relative significance. It's a good way, but yeah, we have to keep in mind that it can be uncertain as well. And then the third point is with the prices, because they are subject to changes and also to uncertainty. And so we have to keep all of that in mind. And with that knowledge, we now know that with generic data and that methodology of social life cycle assessment, we cannot measure an actual performance of a product, but we can identify hotspots for risk. And this is really important because usually the product system and products and product steps and countries and supply chains are so complex. It's a really good starting point to have that hotspots now and to gain deeper knowledge about them. And this is what we did here. And with the help of that methodology, we know now that for a fuel cell electric vehicle, the PEM fuel cell is one major hotspot. And inside the fuel cell, we have the membrane and also the control, which are hotspot components. What we also know now is that the distribution of risk across different countries is, or that Germany is a major hotspot here for 3 out of 5 impact categories. And also that China bears a lot of risk for association in bargaining rights. Now, for the future, it is really important to take these results now and make a broad literature research and to find out more about the data quality. Where is the data coming from? How old is the data? How reliable is it? And then in a second step, look at the indicators and find out if they can really measure what I want to know. And then I have to gain knowledge about maybe special characteristics of a sector, if there is anything I need to know and I need to understand in order to interpret the results in the right way. And then, of course, it would be really interesting now to consider even more stakeholder groups, and with that consider more impact categories and more life cycle stages. In this case, it would be really interesting to use site-specific data, of course. And with the help of that, we could also increase the level of detail of the car components and make a deeper analysis of it. And then it is really important to make a sensitivity analysis in different terms, but for example, by changing the location of production, but also when it comes to the underlying data and the sectors we have chosen for the calculation here. So I hope I could shed some light into the social aspects of fuel cell electric vehicles. I'm really looking forward to receive your questions now, and maybe we can discuss a little bit about that.
Thanks very much, Sally. Very interesting presentation. We're going to move on to our next presentation, which is going to be given by Professor Stuart Hillmansen from the University of Birmingham. Stuart is a professor of railway traction systems within the Department of Electrical and Systems Engineering. He also leads the Rail Traction Systems Group. His main area of research interest is in hybrid traction systems for use in railway vehicles. He is a member of the Birmingham Centre for Railway Research and Education. Stuart's going to give a presentation on the impact of hydrogen standards on the UK transport system. Over to you, Stuart.
Thank you very much, Tony. Hope you can all hear me okay. So yeah, I'm going to be talking about safety standards for hydrogen. It's related to transport, but the main sector is on rail and how rail can kind of learn from other transport modes as well. So it's been really interesting sitting here listening to the presentations we've had so far, and just to see how far hydrogen has come as a viable energy source, energy vector, fuel, whatever you want to call it, for providing propulsion power to a whole host of sectors. So I'm work at the University of Birmingham, and my team were involved in the Hydroflex project, which delivered the first hydrogen train onto the UK mainline. And as part of that work, we obviously had to do all the engineering work, designing it, making sure it worked, developing control systems and so on. But also a big part of that was about understanding how we proved and ensured the safety of the system. And it can be said that the engineering is advancing rapidly. Trains are being developed at a pace, probably faster than what's happening in terms of like the standards keeping up. So we're going to be talking about that in this presentation. So we were funded as part of the Durham University project, the EPSRC funded project, and it was myself and colleagues from TRL that were involved. Here are the names of the people involved. We formed a collaboration to deliver this work on hydrogen standards for rail and transport. Part of the work that we did was about understanding the landscape, what standards were in place, what could be used, what could be transferred from other places and so on. Obviously, we're very grateful for funding from EPSRC. And the output of the work was a high level sort of safety requirements and identifying some of the barriers that existed for safe operation of hydrogen in rail. So I think we've achieved a lot, developed a community of people who are interested in these areas and working alongside sort of the engineering and also sort of the economics and policy people and experts in terms of delivering hydrogen into the rail sector. I think we've found that there's still a lot of work to do and probably a space for the likes of EPSRC and other sort of impartial organisations, if you like, to provide forum for stakeholders to come together and work together. And I think universities are particularly well placed to lead this because we're not necessarily competitive commercial organizations, and I think it's important that this happens, because if we don't work together, we're at risk of developing technologies that won't be compatible, and then further down the line we end up with problems because of interoperability or just the different ways the engineering has played out. So I think doing this early is a really good thing and will ensure the adoption and deployment of hydrogen technologies works really well. One of the big parts of the project was to hold a stakeholder workshop, and TRL led this activity. And we pulled together a community of expert stakeholders who all had an interest in the application of standards to sort of railway hydrogen projects. And I think this was really, really successful. And within that workshop, we developed, and presented the current state of the art in hydrogen standards and policy, how the existing safety framework was used in rail and how we used that framework to understand how we could use hydrogen in a rail environment. And we provided attendees the opportunity to hear the latest research and in the field as well. I think a key outcome from that is the development of a community for further engagement among stakeholders, and certainly myself and my team at Birmingham are keen to keep that work going. We're hoping to hold further events at the university where we bring together people in this area for workshops, for networking, and so on and so forth, just to make sure we keep the momentum going and keep working together on areas that are common across the different actors in the field. And I think it's a careful balancing act, because there are commercially competitive interests here, so people need to retain competitive edge over the competitors, but I still work with them to make sure they've got this a level playing field, as it were, and I'm keen for that to carry on. We also engaged with Railway Safety and Standards Board through this project, who look after standards for the rail industry, and they're obviously right at the heart of a lot of the standards development related to hydrogen technology in rail, and I think they're keen to take the work that we've done to disseminate it as well, and to make sure that people get to know how it's been done so far, and what the gaps are, and what the further research areas are. So just to give you a bit of background, so obviously we all know all this. We need to do something serious by 2050, and the rail sector is keen to get rid of diesel-only trains by 2040. That's not that long away, really, in railway terms. Rail vehicles have got a life of around about 40 years. Indeed, if you travel on the West Coast Main Line, for example, on the Avanti trains, they still feel new to me, and they're 20 plus years old already. And you'd expect them to be around for another 20 years before they reach the end of their lives. So rail systems have got a very long lifetime. And the decisions we make today are going to have impacts well beyond 2050. Rail vehicles could be, that are procured now, could be operational well beyond that. So we need to make decisions today. Hydrogen in the rail sector has seen a massive growth and a huge amount of interest in it. Indeed, yesterday I attended a trade fair in Germany. It's probably the biggest trade fair in the world of railway systems. There's thousands of people descend on Berlin and share the latest technologies in rail, and it was very interesting to see the profile of hydrogen at that event. There are at least 3 hydrogen trains showcased there. I've got some pictures of them at the end. So this is moving rapidly. Indeed, 4 years ago, when it was last held, this event, there was a lot fewer and lower interest in hydrogen. And certainly issues like decarbonisation weren't at the forefront, but that's certainly changed now, and I expect in coming years it will just accelerate even further. So the work we've done at the university previously, this is probably what we're most famous for at the minute, is the work we've done on the Hydroflex train. So here we see an existing train that had a new traction system developed by my team in partnership with Porterbrook, and we installed a fuel cell battery system into this train. And so we did the engineering work, but also the approvals work in order to get the vehicle running onto the main line, and that's what I'm going to tell you about shortly. So that project was launched at the last InnoTrans, which was in 2018, so pretty much four years ago. And it's a partnership between ourselves at the University in Porterbrook. It was an existing train that we took and converted it to hydrogen to demonstrate that we could do it. So I've got some slides on the Hydroflex train itself. So it was the first full-size hydrogen-powered train. I've got full-size in brackets there because my team at the university had developed a narrow-gauge locomotive back in 2012 and showcased that. And that actually, the little train that we developed back then kind of captured the imagination of the rail industry and realized that actually you could do this at a full scale as well. We did a lot of work on disseminating and demystifying the technology before we translated it into mainline scale. So the work involved converting an existing train, which it took the first ever 319 train, 319001. It had already done 2.5 million miles, so it was kind of retired, and then we unretired it and brought it back to life and converted it into a hydrogen train. One thing to note, which is interesting about rail vehicles, is because they have such a long life, it's quite common for a vehicle to get overhauled and refreshed throughout its life. New interiors, new traction systems, new equipment, and so on and so forth. So what we're doing is not out of the ordinary. It's quite common for rail vehicles to get that massive engineering overhaul. Another key thing is these vehicles have already got an electric traction system, so we were able to interface the fuel cell battery system into the existing DC link on the train, which made our lives a bit easier. So lots of rail vehicles, electric rail vehicles that already exist and maybe close to retirement could be good candidates to get converted to hydrogen and extend their useful life by making them an autonomous vehicle. So what we did for the first trial for Hydroflex was to take all the equipment out of all of the passenger seats out of this vehicle MSO, which sits in the center of the train. That's a vehicle that has all the traction equipment on it and traction motors. So there's 4 traction motors on the train. All the others are trailing axles. These traction motors are DC traction motors run from a chopper control, and we took the seats out and made effectively a locomotive carriage in the center of the train, providing all the propulsion energy. That consisted of a battery, 650 volts roughly, a fuel cell with a DC to DC converter, hydrogen storage tank, 24 volt control system, and then a place for us to sit and just monitor things. So the reason we did this was twofold. One is because we did this project. Well, it was kicked off in Intertrans in September, and we had the train running the following June. We sort of kicked the project off in earnest and engineering wise in about the November, December time. So really it was 6 months of really hard work to do this. So we didn't have a lot of time to package the equipment underneath the vehicle. And additionally, having it like this was enabled us to showcase the technology. And we had a walkway along the length of the train, and several thousand people probably walked through the train to have a look at the fuel cell and storage tanks and so on, which was very, very empowering in terms of demystifying the technology. So there's some pictures of the inside of the train, and this does relate to standards here. So the train has got various, it has been designed to meet various structural integrity standards. So here you can see we took the seats out of the train, and the seats are actually attached to the train with very strong mounting points. So the rails in the floor that the seats are attached to are very strong. Having said that, we used those fittings, but had to interface various rafts and other mechanical devices to ensure that all the equipment was attached to the train in such a way that it would meet the relevant standards. So you can see some of the frames and rafts that were created there. The tanks are 350 bar tanks, and here we designed it to EC79 standards using technology and standards that adapted from the automotive sector. And here's the fuel cell. So a fuel cell is just a box with hydrogen going in one end, and some balance of plant, air handling, cooling, DC to DC converter taking the electricity out of it, and controlled with CAN bus messages and some hardware signals that we wrote. We developed some electronics and software to run the fuel cell, to manage its power flow into the train system. And of course, there's battery as well. So pretty much every fuel cell system has a battery. So this one was I think 84 kilowatt hour battery pack, running at 625 volts, providing the DC voltage that was required by the train. And here's a picture of the way we refueled the train. So we took some a standard BOC NCPs and put it through fuel cell systems refueler in order to decant it into the train. So that was our refueling method at the time. I'm going to skip through this quite quickly. This just shows some of the power system architecture. We basically have a battery that provides a DC link voltage, and we run the fuel cell as a current controlled current source converter. So we control that through a T point, and it can either charge the battery or provide additional power to the battery when we're taking traction. So it's kind of independent then, in the sense that the dynamics of the power are all managed by the battery, and we just decide when we need to support the battery by charging it, and so on. So there's quite a lot of work gone into the architecture of this and the control system that I could tell you about. So in terms of safety and standard, we use this thing called the Common Safety Method. It's a basically European standard for doing railway approvals, and allows you to make engineering changes to railway infrastructure and trains. We have an accredited body that does an independent assessment then of it, and we also worked with the Office of Road and Rail, or Rail and Road, I never know which way around it is, who accepted our technical approach of using the Common Safety Method. And that includes doing basic hazard identification, where you go through line by line of every single item of equipment and look at what hazards they might be, and then identify evidence to close out those hazards. So I would say actually doing the safety approvals work was harder than actually the engineering building the train. It took longer and was more expensive than the train engineering. And that we produced an attestation statement then against 11 different technical standards. Some of them are listed there, structural integrity, electromagnetic compatibility, vehicle maintenance, and so on. And then those approvals. So we need to work with the operator of the train, Network Rail, produce things like statement of vehicle configuration, re-register the vehicle, and so on. So there's a huge amount of work involved in getting this onto the main line. It was led by Porter because they own the vehicle, so they acted as the integrator, pulling all these pieces of work together. Some pictures of the sort of standards that you need to comply with, electromagnetic compatibility standards for rail, and so on and so forth. So this is where we looked into this in more detail about how the existing railway standards, would they be affected by introduction of a fuel cell and so on. And in general, there wasn't any showstoppers in terms of meeting existing railway standards with the adoption of a fuel cell propulsion system. So I think, as I said at the introduction, railways are advancing rapidly in terms of engineering. The standards are trying to keep up, but I'd say the engineering is happening quicker. There are standards being developed for rail specifically, but they're in draft form and proceeding at a slow pace, in my view. But that's the way standards go, I would say. As part of the work, we looked at a framework and mapping of existing standards, and we produced this standard sign of landscape, and this is available on a website, and you can kind of click on these buttons and then drill down into the various standards that you need to think about when you're doing fuel cell vehicles. And we're hoping to get this hosted on the Railway Safety and Standards Board's website in the future, because they were quite pleased in terms of how it could be useful for other people working in railway fuel cells to follow the method that we've used. And so that broken down into things like refueling and depot arrangements, how we handle the fuel in terms of delivery, transporting it on trucks and so on, and then handling of the fuel and the interface with the train and so on. So all these things are important. The vehicle is, that's the thing we focused on heavily when we developed the train. So things like electromagnetic compatibility, structural integrity of the equipment, and so on and so forth, making sure that, equipment can cope with the loading and vibration and acceleration environments that a train might throw at it. And then things like hydrogen safety systems. Here we drew on automotive, industrial, and existing energy standards here to install the hydrogen system in a rail environment. And then things like supporting systems, fire safety. This is a big issue. Integration with other onboard systems to allow easy transition to hydrogen, and how we integrate it with the existing propulsion system. So I just kind of had a canter through this. I think the project was very useful because it allowed us to take a step back and look at the current understanding of hydrogen safety standards, how they've been applied to rail, and the work that we've done at the university, and also the likes of the Scottish hydrogen train, which has recently started running, have all have to go through the same pain really, and to make sure we can do this safely. I think we found out there's still some really big gaps, and in terms of particularly over the infrastructure and you manage trains, for instance, in covered environments. So taking trains through tunnels or taking them into underground stations, we really need to think about how we manage that going forward. There aren't any. There's an understanding of that, but I think we need to still work on understand how we manage a rail vehicle traveling in a more enclosed environment. So, Jess, that's me. Thank you. There are, as I said, things are happening at pace. So yesterday I was in Berlin, and that's me in front of a hydrogen train, and that hydrogen train didn't exist a few years ago. It was just a pipe dream, and the one you see in the center is going to go to California. It's a Stadler train that will operate in California, San Bernardino area, and they've ordered 2 initially, and I think there's a follow-on order for several more vehicles. The top right is the Alstom Island. This is a train that's been running since 2018. It recently did a long distance record. I think it nearly went 1,200 kilometers on one charge. And then on the right is a Siemens train. So things are happening quickly. But thank you very much.
All right, thanks very much, Stuart. I look forward to traveling on one. So the next presentation is by Panagiotis Manias. He is from University of Southampton. He's a mechanical engineering graduate from Southampton. He's interested in various engineering activity, including marine and automotive industry. He is currently a research technician within the Maritime Energy Engineering Group, working in the area of alternative fuels for shipping, which includes hydrogen. Over to you.
Representing the University of Southampton, I will be presenting on behalf of Professors Stephen Turnock and Dominic Hudson as well. And to start this presentation, I would like to mention some of the current challenges in the maritime sector in terms of decarbonization. So we all know that strict emission regulations are imposed by the IMO within the maritime industry to mitigate the global warming effect. There is a reliance on fossil fuels due to cargo, propulsion, range, reliability, and cost of maintenance requirements. And those requirements include research and development as well, which results in hesitance when it comes to transition towards cleaner powering solutions. So there is no clear path yet as to what would be the best alternative fuel and powering method due to lack of evidence, as in hard proof and tests carried out by multiple industries. And then there is also the possibility of having more than one ideal solution for each marine application, and that develops controversy amongst any proposal made. Finally, despite hydrogen's potential to be used as a fuel in many powertrain alternatives, it is stigmatized as an expensive to store and utilize fuel source, as well as quite dangerous to handle. Consequently, the challenges that we face as a decarbonization research team are to minimize vessel emissions by eliminating their reliance on carbon-intensive sources, explore ways through which carbon could be used and traded around the world, investigate storage and utilization methods of liquid hydrogen on board vessels, compare that fuel alternative to other fueling alternatives, look into possibility of long distance shipping with liquid hydrogen as fuel, and finally meet the clean maritime aim to become net zero by 2050. Some examples of our recent work include the zero carbon baseload for large vessels and the ammonia marine-powered uncrewed surface vessel. Both projects were under the Clean Maritime demonstration competition and were funded by the Innovate UK fund. So other local projects that we carried out independently were the design of a liquid hydrogen carrier. We carried out a feasibility study of hydrogen fuel demand and distribution, with the case study being the Port of Southampton, quite local to us. We have completed a lot of towing tank testings, fuel cell testings as well, and we've developed dynamic models of hybrid powertrains with fuel cells and batteries. So the first big project that we were involved in was the zero carbon baseload power for large ships. We've investigated the feasibility of replacing the LNG generator sets with smaller ones and adding solid oxide fuel cells to provide the hotel demand on board. To do this, we developed a dynamic energy model, which included the fuel cell system itself, the batteries, and the generators to get the fuel consumption and emission benefits from it. Those models included the safe return to port requirements, a waste heat recovery system, and we've also examined the cold ironing alternative, which is basically a plug-in solution for vessels when they reach port. Of course, during the design process, we've looked into all of the safety requirements and risk assessments involved into undertaking such an action. More important to this presentation, we've investigated the transition from LNG to hydrogen, as many believe that LNG will be part of this moving on process. And finally, we developed a roadmap for multi-megawatt marine solid oxide fuel cell systems. So this is the vessel in question, the one that we based our analysis on. Some of the partners involved in this project were Lloyd's Register, Ceres, the fuel cell manufacturer, Carnival, who provided us with all the data for the cruise ship in question, and Shell, who provided also part of technical information when it came to accommodating that design on board. So the vessel in question has 62 megawatts of installed power. The average port load was estimated to be 9.2 megawatts with a max speed of 22 knots, propulsion power of 37 megawatts, and 6,600 passengers on board. And the reason why I'm saying this is because it turns out that a big part of that load was in terms of heating, ventilation, and AC requirements. And to meet those requirements, we had to base this off a 10.5 megawatt solid oxide fuel cell system. That system would be powered from LNG, which that LNG would be internally reformed into hydrogen, and that would then be later on utilized by the solid oxide fuel cells. Now, for this reforming to take place, a good thing about solid oxide fuel cells is their electrolytic structure, which requires them to operate at above 500 degrees Celsius. But there remains the question that do we really have enough heat for producing steam for many activities on board? So our hypothesis was that we could indeed recover that. So the system design, based again on the original general arrangement of the vessel, we added 10 more meters to accommodate that fuel cell powertrain on board, plus the batteries. So again, from the 4 big generators, we would substitute 2 of these into 2 smaller ones and keep the solid oxide fuel cells on board. And the reason why we included batteries in the first place was to cope with the rapid changes in electrical demand on board, because the ramping up and down rate of the solid oxide fuel cells is much lower than that of the generators. So we had to take that into account. The results of this project were, in terms of CO2 reduction, 35% reduction, still when using LNG as fuel in CO2 emissions, 62% reduction in terms of CO2 emissions when using hydrogen, and 23% when using the cold ironing alternative. But still, there was not enough heat. So in all of these results, we included an additional 300 tons of LNG to meet that steam demand in terms of energy. Moving on to the next project, the ammonia marine powered vessel. Our tasks were to estimate the powering system demand and design a powertrain to aid towards the transition from fossil fuels to alternative options. One of them being, of course, hydrogen, as it ended up being. Then we would carry out some experiments on the hull at a model scale, as well as some of the powertrain's components. And finally, we would investigate the possibility of establishing a zero-emission coastal highway as a side activity of this project. So the vessel that we based our project upon was the Armada class vessel. The Armada class vessel is currently a vessel that is being used by Ocean Infinity, one of the partners of this project. And Oxgreen was the technology supplier in terms of the ammonia cracker, that since this vessel would be powered by ammonia. A couple of specs as well. We were looking into a max speed of 15 knots and a propulsion power of 2.5 megawatts supplied by proton exchange membrane fuel cells. In terms of work carried out, towing tank experiments were carried out under several sea states to calculate different energy requirements for a given trip. That trip being Southampton to Liverpool. So on the right, you can see the system architecture when it comes to the powertrain propulsion system. And to simulate this operation between the ammonia cracker and the fuel cells and the batteries, we again developed a dynamic model. And hence we estimated the total fuel requirement and the battery capacity to cope again with the rapid fluctuations in power demand as a result of the sea states. A 6 degree of freedom platform was employed to study the performance behavior of those fuel cells when undergoing ship motion. And again, that was based on the sea states that we gained from the towing tank experiments. And finally, combining all the results above, we managed to establish a zero carbon coastal highway to reduce, as a way of reducing pressure on the rail and road transport. So the results were that in terms of ammonia cracking energy requirements, 25% of the total installed power of the fuel cells would have to be taken away to just crack the ammonia into hydrogen to power the fuel cells. And hence we provided different alternatives, the main one being liquid hydrogen storage on board. It turned out to be a much better solution in terms of space and weight than the ammonia cracker and ammonia storage, and overall more efficient as well, as the energy requirements to do this were nowhere near close. Carrying on, using the towing tank data, it was indicated that there is a significant propulsion variation when going under heavy weather sea state conditions. And again, we required the batteries to cope with that. Finally, the potential of establishing a zero carbon coastal highway shows that there would be a reduction of 60% in terms of emissions when it comes to transporting goods around the UK. Again, as part of local projects undertaken, there is the feasibility study of fuel demand, hydrogen fuel demand in the port of Southampton. Our aim of this study was to estimate the hydrogen fuel requirement in terms of bunkering for a given port, that being the port of Southampton. Hydrogen fuel energy would be translated in terms of megawatts of electrolysis required. And finally, a bunkering method would be proposed to cover that demand whilst in port for all vessels. So the method that was used in this case, we sampled daily ship traffic of that port, and we used that sample to analyze and distinguish between different types of vessels and their characteristics, main ones being passenger capacity, cargo capacity, speed, and destination, so as to estimate the total energy requirements for each vessel. And then by doing this, we use the annual data that could provide us with each type of vessel that would go into and out of the port of Southampton to get a better picture of what would that mean in terms of total hydrogen energy requirements. So the results of that were that a prediction of 2.8 million tons hydrogen would be required to refuel every vessel that would come into port, assuming that refueling would undergo at every port stop. That mass fuel demand was translated into an average of 40 megawatts of electricity to power electrolysis. Again, locally, the proposed method of storage was with 2,800 meters cubed tanks within the port, and The main refueling method proposed was with small bunkering vessels as a way to avoid extensive costs for building separate terminals to refuel vessels. Plus, it would be a lot easier for smaller vessels as well as luxury yachts to be refueled while in the port of Southampton without having huge queues, I suppose. Finally, one of the big projects that we've undertaken in the past, it was the design of a zero-emission liquid hydrogen carrier, with the main objectives being to develop a ballast-free hull, utilize the cargo as the powering source as a way to be zero emissions. And one of the challenges, some of the challenges that occurred along the way were ship stability due to hydrogen being 6 times lighter than LNG, which resulted in a large weight reduction around amidship. How to power the return journey was also one of the challenges because, well, if there is no cargo on it, once we reach our destination, then we should look and include different ways of propulsing a vessel. So in terms of ship safety, it is known that hydrogen will ignite at all ambient temperatures and at various air content ranges, as an indication between 4 and 74%. The finalized liquid hydrogen carrier was completed after 3 months and under close cooperation with industry specialists, one of them being Shell. And the main outcomes of that project were to develop a feasible ballast-free hull design. We explored the possibility of having large-scale hydrogen transportation and examined the possible shortcomings, main one being storage and insulation properties, since, well, hydrogen is stored at minus 250 degrees compared to LNG being stored at minus 160. And finally, we proved that the cargo boil-off gas would be utilized in a great way to propel the ship forward, but there should be a balance between the cargo boil-off rate and the energy requirements, since the more cargo boil-off, the energy requirements to propulse the vessel, I might add, since any excess cargo boil-off would have to be reliquefied, adding more energy requirements overall to the system. In terms of concluding remarks made, liquid hydrogen looks attractive as a potential future fuel for the maritime sector, even for long-distance shipping and large vessels. Hybrid fuel cell systems with batteries are likely to be more efficient and if possibly the best way to move forward with new build vessels. Ensuring bunkering and liquid hydrogen supplies should be developed alongside future vessels to also ensure an effective transition towards hydrogen-powered transport. Of course, that was one of the main outcomes of one of the projects. It seems that it is technically feasible to develop liquid hydrogen carrying and supplying vessels. And finally, there should be a distributed generation of liquid hydrogen from local renewable resources, and that should provide an effective solution for ship bunkering. That concludes my presentation, and I'm looking forward to your questions.
Thank you, Pana. We'll move on to the next presentation. Last but not least, presentation by Amber Conway. Amber is a recent graduate from Durham University, where she studied engineering, specializing in electrical and then renewable energy systems. Having completed an internship in both hydrogen for transport and recycling processes for perovskite photovoltaics, Amber has recently begun a new role as a consultant at Element Energy. Within this position, she will be working within the hydrogen team to deliver low carbon solutions to a range of different clients, applying her understanding built through her dissertation project and the potential of hydrogen for marine end use and the implications on the standards creation. Over to you, Amber.
Thank you, Tony. So hi there, I'm Amber, and I'm going to be presenting some of my research today, which I've worked on with Dr. Jane Chin and also with Anthony as well. I will be exploring the potentials of hydrogen for maritime end use, from analysing demand in container vessels to understanding the implications on standards and the standards landscape. So it's no secret that moving towards decarbonisation across all sectors, there needs to be a massive push in considering how to address those which are harder to abate. Following off from Pano, there's one such sector being the maritime industry. Alternative fuels such as hydrogen and its synthesis products, methanol and ammonia, have potential to fill this niche in decarbonising marine vessels because they're often unsuited to batteries due to their inhibitive size and weight. Through the course of this presentation, I will discuss some of my research, including a literature review of the state of the art of hydrogen as a marine fuel and exploring hydrogen synthesis products, ammonia and methanol. There will be 3 uptake scenarios which I will explore, including the introduction of these 3 fuels within the UK container vessel fleet. I will then review the implications of the results of these scenarios and my research in the supporting standards landscape which followed. So first off, I conducted a literature review in the state of the art. In understanding the potential of hydrogen and its synthesis products, it's really key to consider this. Some key findings are summarised here as I will now elaborate. References for the literature review will be on the following slides and can be sent at request. So within the literature, there currently exists significant research into the feasibility of hydrogen as a marine fuel, particularly concerning the production, energy and space requirements of hydrogen. The cleanness of hydrogen has also been frequently considered alongside other alternatives to traditional marine fuels such as LNG and biodiesel. The issue of storing hydrogen on board vessels, which will be brought up later in this presentation, is regularly discussed and has led to considerations of methods to mitigate the scale of onboard storage, which is demanded by hydrogen-fueled vessels. One of these mitigations could be the onboard production of hydrogen using electrolyzers, but this must produce hydrogen in compliance with the ISO 14687 standard, which regards hydrogen fuel quality. Low carbon hydrogen is a really necessary staple within the literature due to hydrogen's decarbonisation motivation. It's crucial that the hydrogen produced and used in the marine industry is as low carbon as possible. And there are numerous demonstration projects which are detailed throughout the literature regarding marine vessels of different sizes, which come from all different sources, including certification bodies. As a congestion point for hazards, bunkering of hydrogen has been explored through several key studies, which are listed here, considering the suitability of current and novel bunkering methods for hydrogen. And overwhelmingly, it brings back that a modular, scalable and adaptable system should be designed for hydrogen bunkering. Ammonia and methanol are often also considered in their own right, which is important to say, as both can be produced using renewable hydrogen produced via electrolysis, and they feature larger volumetric energy densities, which lowers the storage requirements, which, as I just mentioned, is quite a difficult point in the use of storing hydrogen on board vessels. Ammonia also has large distribution infrastructure, and both fuels benefit from wider existing use and applicable standards. So the references that I've just mentioned and that will appear throughout the rest of the presentation are shown here and can be referred back to. So throughout the literature and within discussions regarding the scaling of use of hydrogen, various colours are actually used to describe the emissions associated. Qualitative labels are listed here, and I've tried to explain them as clearly as possible. Due to the push in recent years by the UK government for decarbonisation, including the publications of the UK Hydrogen Strategy and Report for Options for a Low Carbon Hydrogen Standard, the production end of hydrogen is actually becoming pretty well regulated, with low carbon hydrogen being classified as having greenhouse gas emissions intensities of less than 20 grams of carbon dioxide equivalent per megajoule of LHV up to the point of production. So we have a quantitative standard for the classification of low carbon hydrogen within the UK. However, this varies, and indeed the definition of these qualitative labels varies between countries. So reports such as these are balanced by prevalence in literature analysing the gaps in the supply chain which are not being adequately addressed, whether through consideration or speed. Such analyses include the report on green hydrogen policy and the green hydrogen initiatives, which focuses on existing schemes, including guarantees of origin for low carbon hydrogen. So having given you a crash course in all the literature that has informed my study, I'd now like to move on to discussing the research gap which I decided to address. From the foundation of research, the gap that presented was in regarding the demonstration of the effects of introducing hydrogen as an alternative fuel into the marine fleet and the effect that the uptake of hydrogen in this sector would have on the demand for robust standards and the prioritization of these standards actually as well within the framework that could facilitate the growth of a marine hydrogen sector. And shown here is the explanation of how codes of practice, standards and specifications and regulations interact in the hierarchy of how they function legally. So in order to conduct this project, I needed a pretty robust methodology. You've already seen the systematic literature review, which I conducted. And to conduct this, I used key search terms. And then from this foundation, I was able to then build an understanding of the standards, policies, and certification bodies that were involved in the industry, and of course, the state-of-the-art research. Having established the research gap, it was possible to begin to consider scenarios of the uptake of hydrogen, ammonia, and methanol. It was really necessary at this point to focus on a subsect within marine vessels, and due to their large fuel consumption, which is 22% of marine fuel consumption totaled, and their expected growth over the coming years, container ships were chosen as the suitable group to focus on. 3 scenarios were designed, as I will describe in more detail shortly, to explore different levels of introduction of hydrogen within this subsect. Secondary qualitative scenarios were also introduced to test the assumptions that were made within the primary scenarios. So within this presentation, I'm only going to highlight the key implications due to time. These will focus in on the implications of the study, which consider the realities of hydrogen production and the infrastructure within the UK, and include, as I just mentioned, the testing of assumptions made in the primary scenarios through to secondary qualitative scenarios regarding the import of hydrogen and the use of internal combustion engines. And secondly, implications on the standards, in particularly focusing on 4 stages of the supply chain, which are production, distribution, and bunkering and onboard storage. Now moving on to the potential scenarios which I looked at. So 3 primary scenarios for hydrogen uptake were considered, and a unit ship, which I will refer to as a ship which will be taken as a standard unit and applied to create the estimates for fuel demand and emissions across each scenario. This ship was taken as the CMA CGM Aliaga of the Maersk fleet, and it was chosen as the reference as it closely matched the average container ship size from UK port throughput data. This established a unit ship, which required 1.6 times 10 to the 4 gigajoules of energy over a 4-day voyage, which is used as the standard throughout this research. These assumptions were drawn from a review of the NAEI shipping emissions methodology and data from UNCTAD. So scenario 1. Scenario 1 detailed the emissions reductions targets for the marine sector and acted as if these were being applied to the container shipping industry and met solely by the introduction of alternative fuels, hydrogen, methanol, and ammonia. 3 cases with varying input of these hydrogen carriers were applied, enabling an understanding of different hydrogen demand resulting from the use of different synthesis products. Moving on to scenario 2. We've already discussed how LNG can be used to inform an understanding of hydrogen within the marine industry. So the key assumption within this scenario was that it would be possible for hydrogen to follow the same trajectory as was followed by the introduction of LNG, since they have similar properties and the comparable motivation of emissions reduction. Again, 3 cases were considered, which were initially 1.4% of the total number of global hydrogen ships would visit UK ports once every year up to 2050. Secondly, that all hydrogen ships within the global fleet would visit UK ports once every year. And finally, that each hydrogen ship within the global fleet would make 40 trips to the UK. And this again was estimated in line with UK container ship fleet size and also the total port throughput which was again taken from UNCTAD. Scenario 3 was the business as usual case, which was really important in providing context to the first two scenarios. This represented the emissions reductions potential of the current planned hydrogen production if the amount estimated by the Hydrogen Analytical Annex was apportioned to the marine sector and then proportionally to container shipping. So I will move on to show emissions reduction and hydrogen demand in results section, but for now I'd just like to take you to the current UK hydrogen production. So this shows the timeline for the business as usual case with all planned hydrogen production projects and targets available, which were at the time of writing in May. So if all of these projects were seen to completion, this is the expected UK hydrogen production capacity year on year, increasing steadily. So now if we move on to the basics of the study. In introducing hydrogen and its synthesis products as alternative fuels, it's really important to understand how they compare to one another and to the existing marine fuels that they're expected to replace. So the key properties are shown here in this table. Due to hydrogen's comparatively low volumetric energy density, compression and liquefaction are necessary for storage and for use in the marine sector. And even post-liquefaction, ammonia and methanol have higher volumetric energy densities, as shown here. However, due to conversion processes and lower gravimetric energy densities, it is hard, as demonstrated throughout literature by lack of consensus, to pick a clear front runner among these three alternative fuels. However, since renewable hydrogen acts as a feedstock across the board, this is the driving force of the study, and renewable hydrogen is assumed to be the feedstock for all of these cases. Again, another basic of the study, also fundamental to the creation this time of scenario 2, is the understand and to the potential barriers of introduction of hydrogen, is the understanding of its comparison to liquefied natural gas or LNG. So LNG is another high flashpoint fuel, which was also introduced to reduce emissions, in this case, particularly sulfur oxide emissions. LNG has continued to experience an increasing rate of uptake with over 350 LNG vessels in the international fleet today. And as such, it's really crucial that relevant safety procedures, including risk assessments and detection systems that have enabled LNG's successful introduction, are used to ease and accelerate, where relevant, the introduction of hydrogen as well. So now the good bit, moving on to key results. So first, we're going to take a look at the individual scenarios. From scenario 1, the predicted emissions from the UK container fleet were seen to exceed target emissions, meet reductions targets from 2023 onwards. This then implied that the first year of demand in 2023 would see 5.63 to 9.56 terawatt hours of energy demand to be fulfilled by hydrogen and its synthesis products, depending on the case. Hydrogen demand as a feedstock was determined to be a constant ratio depending on the case of split between ammonia, methanol, and hydrogen. The cases were hydrogen only, equal energy contribution from each of the three fuels, and contribution based on current production levels, where hydrogen is produced in the highest quantity, but ammonia and methanol do not follow that equal split, as was explored in the secondary case. So the latter assume that current production levels implied a level of maturity in distribution and production infrastructure. So although there might not be necessarily immediate transfer of these production levels, you could see that the level of infrastructure might inform a tendency to lean more towards one fuel than another. So scenario 2 actually demonstrated the current lack of feasibility for the high frequency visiting case of hydrogen ships. So this was the 40 trips per year when compared to the business as usual case, which I will discuss and compare further with some graphs to follow. So hydrogen uptake in shipping would currently really struggle to achieve the uptake rate previously demonstrated by LNG without major intervention. A much more tentative introduction would be expected without that. So moving on to scenario 3, contrasting that with a bit of optimism. So scenario 3 offered real optimism regarding the hydrogen production levels, especially in the context of the ever-increasing interest in hydrogen within the UK and globally for a variety of different end uses. In order to harness this momentum we're seeing and see the use of hydrogen within shipping, particularly container shipping, standards need to be built up to support this and support the developments which we'll go on to discuss. So looking to compare the scenarios a bit more now, I would like to further compare the primary scenarios and cases. Here we can see the disparity between the demand from scenario 2 with high visiting frequency and scenario 3 business as usual. So the green soaring above is scenario 2 and the blue but increasing is scenario 3. So this has clear repercussions regarding emissions abatement, which we can now see here. So the 3 bars that sit at the same height, constantly moving up, they represent scenario 1 where emissions targets were met by all 3 cases. And the green represents scenario 2 and 3 is represented again by the small blue, but steadily growing dark blue bar. The gap between target emissions reductions and reductions estimated to result from the business as usual case is 4.3 megatons of carbon dioxide equivalent. So in other words, just over a quarter of reductions needed would be achieved without significant changes to the current production plans using this study. If we now look at the implications of the study overall, so 10 megawatt of low carbon hydrogen production is expected from within the UK. So even looking at the production of hydrogen that incorporates all forms of hydrogen produced. So we really need to see an increase in hydrogen availability to actually allow the scale of decarbonisation demonstrated by scenarios 1 and 2. The infrastructure requirements and technological development need to follow that as well. So the potential for import could support this with Norway, Australia, Spain, the UAE, USA, all looking to import hydrogen potentially to the UK. And depending on the low carbon status, this could really support hydrogen production domestically and could support the growth of the marine sector in using hydrogen as a fuel. It's also important to consider that in this study, fuel cells were explored over hydrogen and dual fuel engines as they create zero emissions at the point of use. However, in the near future, engines would be best placed to dominate hydrogen fuel propulsion in marine vessels. And also to consider that hydrogen, ammonia, and methanol will not be the only emissions abatement technology to be within the marine sector, and they will be supported by a range of other developments, which will also help lower emissions and meet those targets. So if we look now at the implications on standards on regarding hydrogen production need to be defined and production needs to increase, particularly of low carbon hydrogen. Purification should occur at the appropriate stage of the supply chain, as it may occur due to liquefaction, which produces 99.9999% pure hydrogen, and production on board ships from ammonia stock is an additional possibility, and it would need to conform to the same purity standards as required for the end use in either fuel cells or internal combustion engines. Regarding distribution, standards for pressurization, allowable leakage, safety distances and materials are required. Regarding bunkering and onboard storage, risk assessment bunkering procedures may derive from existing standards for fueling stations, which we see with road transport vehicles. Onboard storage standards are underdeveloped, which is an area which needs looking at carefully over the coming years to support use. So the standards framework in and of itself have priority criteria of health and safety, harmonisation, defensibility, enabling market growth, technological neutrality, and sustainability. So all of these need to really come together to work to produce the standards which will support and enable the use of hydrogen within the marine sector and enable the potential that we've seen throughout the previous slides. So in conclusion, we need to prioritise those criteria to create standards and unlock the large potential for hydrogen, ammonia and methanol as alternative marine fuels. The demand for hydrogen from container vessels will currently far exceed current planned capacity. So production and distribution developments are not only necessary, but vital. The timescale of the uptake will depend heavily on this. And to accelerate the process, we will be able to minimise the emissions. Thank you for listening, and I welcome any questions.
Thank you very much, Amber. An excellent presentation. Okay, we've come to the end. Thank you to all the speakers. Thanks for the contribution from the audience in terms of questions. It's been a fantastic opportunity. Run the conference over the last 3 days. I think it's been very insightful and stimulating. And we've had a diverse range of speakers covering all sorts of themes that are representative of the network. So thanks to all of you for contributing and the questions. I'd like to thank Jackie and Rachel, Jackie in particular, for organizing the conference and doing a great job in keeping me on the ball, as usual. We'll also be continuing with our monthly series of webinars. If you would like to present any aspects of relevant research, please do get in touch. We're also compiling a special issue for the Journal of International Journal of Hydrogen Energy. This will be published in the spring next year. So again, if you have any research that you feel could be included, please email us at hydrogen.research@durham.ac.uk. Our next academic conference will be in 2023, next year, and we look forward to seeing you all there again. Thank you very much.